What's happening, dogs? Mr. Allen here with an introductory video to some inverse functions. We have our parent quadratic function and our parent cubic function. We're going to find the inverses of each one of these. We're going to determine if the inverses are still a function, and we're also going to find domain, range, x and y intercepts for each one. So let's get started here. To get our inverse, the first thing I like to do is write it as y equals x squared. Then we're going to switch our x's and y's. So I'll take an x here equals y squared. When you first started dealing with inverses, we had a lot of ordered pairs or like maybe a t-chart, and you swapped your x's and y's, plotted those points. That's our inverse. The same goes with a function. I'm just going to swap my x's and y's. But now what I need to do is I need to resolve this thing for y. So I'm going to square root on both sides here, and I will get myself y equals plus or minus the square root of x. Remember, when we solve using square roots, or any even degree roots, we're going to have a plus or minus, since both say 2 squared would equal 4, but negative 2 squared would also equal 4. Got to account for the plus or minus when you are solving using square roots. All right, so here we go. That is my inverse, so we got to notate it properly. So I'm going to write right below this one here, f inverse of x equals plus or minus the square root of x. So now let's go ahead and plot both of these on the same graph, and then we'll start dealing with these other characteristics that we have here, these other features and whatnot. So for the first one, I will go ahead and plot it in blue. All right, so this is going to be in blue right here. My quadratic function, I know, is just 0, 0. Then I have 1, 1, and negative 1, 1. And then we have 2 squared is 4, so I'll have that point here. And negative 2 squared is also positive 4. I think that's enough there. I'll go ahead and create my lovely quadratic U sort of shape there with a little bit of curvature. Excellent. Fantastic. All right, now we've got our inverse function, which we'll do in green. So we got a couple options here. I could swap my x and y's from the quadratic here. I could also graph my square root function with what I know about square roots and just plugging in some points here. We'll kind of do both as we go through this and connect the dots, all right? So if I square root 0, I get 0, right? So that's going to be a point right here. If I square root 1, I will also get positive 1. And if I square root, say, well, 2's not a nice one, 3's not a nice one, 4, square root of 4 is going to be positive 2. And you'll see how I have the ordered pair 2, 4 here, but now I have the ordered pair 4, 2 here. The x's and y's have switched. But we also have to account for the negative here, right? So 0, still going to be 0, but positive 1 is going to give me negative 1 for the plus or minus. And then I have the 2, which is going to become negative 2 down here. And we have this like sort of sideways looking quadratic, right? But it's our square root. It's the positive and the negative version of that square root. So now let's answer some questions. First one here, is the inverse a function? Well, in order to be a function, I must pass the vertical line test. My quadratic is a function, right? The blue one there, it's only going to pass through the blue one twice, or sorry, only once at any given time. But then my green one here, that's passing through multiple times, right? Twice at any given spot here, except for like at our vertex, right? And then it doesn't exist over here. But at any given time, if it passes through more than once, it's not a function. Okay, so my inverse here is not a function. You can also tell if the inverse is going to be a function or if it's invertible, right? So is the inverse a function, and the phrasing is our function invertible? Those mean the same thing. I can use my horizontal line test. I can see the blue one here does not pass the horizontal line test. Therefore, its inverse will not be a function, or it is not an invertible function, okay? Now in the future, we'll actually restrict our domain so that the inverse is a function. I'll be doing that in another video though, all right? So let's go ahead and talk about our domain and our range here, okay? So for the first one here, we'll do that in blue. My domain is all real numbers here. It keeps getting wider left and right. So I'm going to say x equals all reals. You could also go from negative infinity to positive infinity if you would rather interval notation. I like making the dope r, so I'm going to do that. My range now. Does it ever stop going low or high? Yes. The lowest it gets is 0, including that, and then it goes on up forever. So we can say y is greater than or equal to 0, or you could do, I'll show you guys the two notations here. This would be negative infinity to positive infinity. This would be 0 to infinity. All right? So those are the same things, just different notation. You don't need to put both. Okay. X-intercept. Do I have one? Yes. X-intercept is 0, 0, which happens to also be my y-intercept, 0, 0. It's passing through the origin, so nothing special there. Okay, nice. I like that. How about my inverse now? What's my domain of the inverse? Well, my x's here, I do stop going to the left at 0, so it's going to be x is greater than or equal to 0. My range, it's going to keep going up, and it's going to keep going down as it goes to the right there. So my range is y equals all real numbers. Interesting. They just kind of swapped places, didn't they? Well, my x's and y's swapped to create the function, or sorry, to create the equation. So my x's and y's, all that stuff switches. My domain and range are going to switch because the domain and range are associated with the x's and y's, respectively. X-intercept, 0, 0. Y-intercept, 0, 0. So that didn't change because they were the same thing to begin with. So you're not going to see a change there. All right. Cool. I love it. Fantastic. Okay. So actually, let's talk a little bit about how could we make the inverse a function. What if I were to, like, say, not include, I said, you know what, let's not include, like, this side of the graph, right, the left side. That would then eliminate this portion here, right? So in other words, if I just said, I'm going to restrict the domain, we're going to say the domain's going to be x is greater than or equal to 0. Now I'm only talking about this side of the function here. Thus, I'm only talking about the positive portion of the inverse. Well, now, if I remove that part, the blue one passed the horizontal line test, therefore it is invertible. Its inverse will then be a function. Okay, so there will be problems where we ask you to restrict the domain so that the inverse is a function. Okay, or you might just be given this guy right up here, and then they'll have a little comma. Sometimes they'll do this: f of x equals x squared. X is greater than or equal to 0. Find the inverse and graph it. That way, it is a function. Last thing that I think is very nice to note here, guys, is these functions are reflected. Sorry, these equations, these graphs here, are reflected over the line y equals x. That's interesting. Right? It's a diagonal line, 45-degree angle there, slope of 1 over 1. Right? The blue reflects onto the green over that. It's not like a rotation. It doesn't look like a 90-degree rotation. It would work for this particular one, but not for all inverses. But all inverses will reflect over this diagonal line here, y equals x. And it all kind of connects here if you think about everything here. We swapped our x's and y's to find the inverse. All of my ordered pairs will have the x's and y's swapped. My domain and range, which are associated with the x and y's, all swap. And it's reflecting over the line y equals x. Y equals x, x equals y. It reflects over that line. That is dope. Okay. Enough with the quadratic. Let's head over to the cubic here. We'll go ahead and why don't we use the same color scheme here with this one so it's all kind of the same. So I'll find my inverse here in green. First thing I like to do is y equals x cubed. Swap my x's and y's, so I'll have x equals y cubed. And then I'm going to need to cube root both sides. So you'll see a little 3 on that root there, like chilling in the little check markish looking thing there, the radical. And now I have the cube root of x equals y. Why don't I have the plus or minus of the cube root? Well, when it's an odd root, we don't need that plus or minus, because when I cube something or raise it to the 5th or any other odd power, it retains its sign. 2 cubed is 8. Negative 2 cubed is negative 8. Whereas with the quadratic here, they would both come out positive. So you have that plus or minus aspect that you have to add in there. All right, so I have that one. Now I'm going to write that guy as g with a little negative 1. That is the notation for the inverse, okay? This reads g inverse of x. All right, so the inverse of g of x is the cube root of x. So let's plot these. I'll plot the original in blue. So I've got it at 0, 0. 1 cubed is 1. 2 cubed is 8, which is right up here. And then negative 1 cubed is negative 1. And then we'll have negative 8. I'm going to get right into my g of x function there. All right. So now let's try to connect these dots in a lovely way. Looks pretty decent. All right. So there's my cubic function. parent function, right? We can have a whole bunch of different things going on with these. But now let's go ahead and graph the cube root function. So we could do so by just swapping our x's and y's, because we know this is the inverse. We found the inverse. We know the x's and y's will swap. But let's do it with just like plugging numbers in and see if it also lines up with the switching of the x's and y's. I think that's kind of cool to examine that. If I plug in 0, the cube root of 0 is 0. Cube root of 1 is 1. Cube root of negative 1 is negative 1. Now, we could cube root like 2, 3, 4, 5, 6, whatever, any of those. But the next perfect cube after 1 would be 8. And then after that, it would be 27, right? Cube root of 27 is 3. But we're not going to have room for that on this graph. So 8, I did have enough here for 8. The cube root of that is 2. And the cube root of negative 8 is negative 2. And look at that. I have 2, 8 here. I have 8, 2 here. I have negative 2, negative 8 here. I have negative 8, negative 2 right here. Now I'm going to connect these dots. And we see this thing, this one's clearly not just like a rotation. Like this is a rotation of 90 degrees, it looked like. But here already we see like a situation where a rotation would not work for every single function. But it does still appear, that it has some symmetry, aka reflects over that line y equals x, doesn't it? You kind of see it where it's like this guy like it twists almost. I don't know, it's hard to visualize, but it to me, like when I see it, it makes sense. Hopefully you're seeing this symmetry as well as I am. But we do see how these points will jump over the same distance to the pink line, same distance here that they're reflecting over there. Okay. So now let's talk. Is my inverse a function? Well, the blue one is my original. We knew that was a function. We were told that it's a cubic function, right? Then the cube root. Well, does the green one pass the vertical line test? Yeah, it does. So these are both functions here, right? So both of them are functions. Here, the quadratic, the inverse of it was not a function. Here, the inverse of the cubic function is a function. Cool. Now let's talk domain and range. Well, domain of my original, it's here. I keep going up and to the right, down and to the left. So that's going to be all real numbers. My range, if I keep going up and I keep going down, that's also all real numbers. My x-intercept and my y-intercept, because you don't have any transformations right now, they're all passing through the origin. So this is going to be 0, 0 for both. Kind of boring, but whatevs. Now let's go over to the inverse. Well, I'd imagine we could see it being all the same, right? If my x's and y's switch, my domain and range switch, but they're still the same. So they're going to be the same thing. But just take a look. I keep going to the right. I keep going to the left. That's all real numbers. It keeps going up and it keeps going down. All real numbers, right? So, x. X equals all reals. Y equals all reals. And then I am passing through the origin. So both the x and y intercepts are 0, 0. Nice, man. It's awesome. So there we go. A little introduction. We got our parent functions. We've got the inverse of those as well. They clearly reflect over y equals x. That is going to be the case for any inverse. So if you're ever graphing and you're like, this doesn't look like it reflects over the y equals x, it's kind of hard to tell. Like when you see it, you'll know it doesn't reflect over that y equals x. It will look like something's off. Okay, so I like to always draw that y equals x line on there, or at least like hold up my pencil or my markers and be like, does that look like it's right? You know, it's a good little visual check. All right, that's it for this one here, guys. I'm going to do some other videos with some transformations in here. So you're going to have, you know, shifting up, down, left, right, see how that affects the graph, and also do some domain restrictions on our even degree functions that need it. So that way the inverse is also a function. So this is just a start. Keep watching these videos. Make sure you like it, subscribe it, share it, and stay dope.